In this SQL list, for each select statement, the sum of percent CPU and percent IO is roughly 100%. But for insert statements, the total is much lower than 100%. So what's going on behind the scene? The SQL statistics section of an Oracle AWS report presents top SQL lists from different angles. Before we begin to analyze these lists, we should find out how many SQLs were captured. In this top SQL list, it states captured SQLs account for 0.2% of total DB time. In this case, analyzing the list would be almost a waste of time. However, it can be tricky to judge the representativeness of captured SQLs. In this example, Oracle states captured SQL account for 59.2% of total DB time. At first glance, one might assume 40.8% of SQL execution time is unaccounted for. However, DB time isn't the same as SQL execute elapsed time. We scroll up to Time Model Statistics section. It reveals that SQL execute elapsed time makes up just 67.83% of DB time. Thus, the maximum possible capture is 67.83% of total DB time, not 100%. Calculating 49.2% divided by 67.83% gives roughly 87%. This means the captured SQL represents 87% of the total SQL executed elapsed time. It's quite a representative sample. On the other hand, since captured PL/SQL execution accounts for 67.5% of total DB time, we can infer that nearly all SQL were executed within PL/SQL procedures, and all major PL/SQL procedures were successfully captured. Why the SQL percent total sum exceeds 100%. In this example, we add up the percent total column here. We get 116.45%, more than 100%. This happens because SQL statements executed within PL/SQL get counted twice. Once in captured SQL, 49.2% of total DB time, and once in the captured PL/SQL, 67.5% of total DB time. The combined total of these captures is 126.7%. There is an approximate 10% gap. This gap is understandable. Oracle leaves out SQLs that account for less than 1% of DB time, and does not include line SQL operations performed within PL/SQL. Missing SQL ordered by row processed. You might have noticed that in the secret statistics section, there are several top secret lists. Things like secret ordered by elapsed time, secret ordered by CPU time, and so on. But for many people, one important list seems to be missing. Secret ordered by rows processed. Fortunately, there is a workaround. The list called secret ordered by executions includes two useful metrics: rows processed and rows per execution. The fewer rows a query processes, the more efficient it usually is. In fact, the ideal rows per execution value is 1, meaning each execution processes exactly one row. However, if we zoom out to a system-wide performance view, this one execution per row approach isn't really efficient. A better approach is to use array fetching or batch processing, where each execution retrieves multiple rows. For example, imagine each execution fetches 100 rows. This means you will reduce the number of executions by 100 times, and fewer executions mean less overhead. That's a big performance win. The last list in this section is the complete list of secret text. It shows the full secret text for every secret ID in the report. When people go through this list, they often ask, is this secret coming from PL secret, or is it a standalone secret statement? Here's how you can tell. If a secret statement is invoked by PL secret, the PL secret interpreter rewrites the entire secret text in uppercase. That's the first sign. The second clue is in the variable names. Input variables show up as :bn, like :b1, :b2, :b3, and output variables show up as :on, like :o0, :o1, :o2. So with these two hints, all uppercase text, and those :b or :b variables, you can easily spot which secrets are being called from PL secret. When it comes to secret generated internally by Oracle, there are few ways to support it. First, you'll notice the secret text is usually in lowercase. Another hint comes from Oracle's naming conventions. Many internal objects have names that end with a $sign, the dollar symbol. And for columns, which Oracle uses to store numerical identifiers, you will often see a hash at the end of column names. Once you know these patterns, it's pretty easy to tell internal secret apart from user secret. There's another interesting thing to keep in mind: the cursor sharing parameter. When it's set to false, Oracle rewrites secret statements that use literal values. It replaces those literals with system-generated bind variables. They look like sysb0, sysb1, and so on. This trick lets different secret statements that only vary by literal values share the same cursor. That means fewer hard passes and better cursor sharing. For healthy secret statements, the sum of percent CPU and percent IO should be pretty close to 100%, because any time spent on elsewhere, outside CPU or I/O, is basically wasted. In this list, for all select statements, the sum of %CPU and %IO is almost 100%. It looks perfect. But if you look at the insert statements in the same list, the total drops way below 100%. So what's going on behind the scene? To figure it out, let's move on and check the top wait events. Here we see 3 significant waits besides CPU and I/O. Logfile switch checkpoint incomplete, buffer busy waits, and logfile sync. These waits mostly affect insert operations, not selects. The two redo related waits, logfile switch and logfile sync, are caused by the redo generated during inserts. And the buffer busy waits happen when multiple sessions try to insert into the same data block at the same time. So there you have it, mystery solved.